Okay, so we're going to talk about multiplying radicals a little bit more tonight. This starts on page 399 in your workbook. This is going to be an extension of your multiplication of radical property that we were introduced to last week. And let's do a quick review of that property. It says if you have the square root of a times the square root of b, that you can write this as the square root of a times b. And it also works the other direction. You know, equations always work both ways. So if you have this, then you can break it up into that. And so that's where we're stemming from, is the rule that we learned last week. Concept 1 at the top of page 399 starts us with the square root of 7 times the square root of 5. So according to this rule, that says that we can do 7 times 5, which is 35. They're both underneath square roots, so that's legal to do that. Any questions? Okay, if we had one like the cubed root of 2 times the cubed root of x, we could write that as the cubed root of 2 times x, which is just 2x. The review and complete: radicals can be multiplied if they have the same index and the individual radicals are real numbers. So another example would be the square root of 5 times the square root of 20x. So if we use our multiplication property, that says 5 times 20 is 100x. And then we can take the square root of 100. What is the square root of 100? 10, but we cannot take the square root of x. So we're left with 10 times the square root of x. If I gave you one that looked like this, 4 root 6 times 2 root 15. Now this one is interesting, it's all numbers. So I would need to multiply the 4 times the 2, because those are both outside the radical, and then I can multiply what's underneath the radical times each other. So 4 times 2 would be 8, and then underneath the radical, 6 times 15 is 80, I believe. Somebody check me. No, 90. I do that every time. 90. Let me clean it up a little bit. Okay, now we learned last week how to break 90 down into a perfect square times a non-perfect square. I know that 9 is a factor of 90, and I know that 9 is a perfect square. Well, how are you going to know that, Mrs. Hopkins? Well, you're just going to have to start thinking that way. That's what we're trying to do, is train our minds to think that way, okay? So if you see 90, then you go, well, that's a pretty big number. Maybe it has a perfect square factor in it. Let me go through my list of perfect square numbers and see which one of those might be a factor of 90, and 9 is. So we're going to rewrite 90 times 9, as the square root of 9 times 10. What is the square root of 9? What's the square root of 9? 3. When the 3 comes out, what do I do with it to the 8? You multiply it. It says 8 times this stuff, okay? Well, part of that stuff is 3. So 8 times 3 is 24, and then on the square root of 10. This is a really hard thing for students to do, so just try to work lots of problems. Okay, you need lots and lots of practice on that. You can also look up some, just Google some stuff if you wanted to, if you needed just some rote practice on the same thing over and over. Okay, let's look at this one with fractions in it. 1/4 on the cubed root of xy squared times 1/2 on the cubed root of xy. Again, we're going to do the outside numbers times each other. 1/4 times 1/2 is 1/8, because you do numerator times numerator, denominator times denominator. Then they're both under cube roots, so it's the cube root of, ignore this 3 right here, that's with the problem above it. X times x is x squared. And y times y is y to the 3rd. So can you take the cube root of x squared? Remember, this number has to divide into that number. So can you take the cube root of x squared? No, 3 does not divide into 2, but can you take the cube root of y cubed? What is the cube root of y? And then I have the cube root of x squared left. Okay? All of these problems in this section and the previous section as well say assume the variables represent positive numbers so that you don't have to worry about including those absolute values. Okay, so if you wonder why I'm not putting those, which I know I mentioned that last week, but if you wonder why I'm not putting those, just remember it's because the directions say assume that they're positive. Okay? All right, let's do one where we're going to be multiplying we're multiplying constantly in this section. I shouldn't even say that. We've got 5 times the square root of x times a 3-term expression, 3 square root of x plus 4 square root of y minus 7. Now, this should look to you like the distributive property, where you have a single monomial term on the outside of what looks like a trinomial, so to speak. And you would use your distributive property. So you're going to do 5 square root of x times 3 square root of x. Okay, outside times outside, inside times inside. That's what I always tell my students. Okay, so that's 5 times 3 is 15. The square root of x times the square root of x. It is x simplified. Let's take it one step at a time, though. You're absolutely right. The square root of x times the square root of x is x squared, and Ronnie said that's x. And if you see that immediately, don't write square root of x squared. I just wrote it to make sure I show all my steps, okay? And then 5 root x times 4 root y, and it's positive times positive. So you have to look at the sign in front of this as the sign of that number. That's a positive expression. So it will be plus 20, and then x times y is just xy. And then finally, 5 root x times negative 7. Yes, that's the minus sign, but it's also the sign of the 7. So it would be negative 5 times 7, because 7 is not underneath the radical. You do the outside times the outside, which is 35, and then the square root of x tags along at the end. And then we're going to go back through and simplify like Ronnie said. 15 times the square root of x squared is just 15x. And then I don't see anything else that can be simplified, so I will just rewrite my answer. Okay, just like we use the properties for multiplying polynomials with this, a monomial times a trinomial, you use your distributive property. You're going to continue to use your properties of polynomials throughout multiplication. So everything that you could do for real numbers, you can do for these with radicals, okay? It's no different. So don't think that the rules change. They still are the same. So if you see, do you remember back probably our first week of class, we said if we had x plus 2 times 3x plus 7 what would we use to multiply these two binomials? The FOIL property, and that's all based on the fact that it's a two-term times a two-term, right? A binomial times a binomial. So that property is also the same for radicals, and that's what we're going to do now. We have negative 2 on the square root of 3, which means times it, plus 3 on the square root of 7, times 4 on the square root of 3, minus the square root of 7. So you're going to FOIL this. First times first, outer times outer, inner times inner, last times last. So first times first. Negative 2 root 3 times 4 root 3. Negative 2 times 4 is negative 8. And the square root of 3 times the square root of 3 is 3. Okay, is that all right for me to jump to that? Or do y'all want me to write the square root of 9? Thumbs up if it's okay for me to jump to that. Thumbs down if you want me to write the square root of 9. Write the square root of 9. Okay. I always cater to if someone wants me to do it because I don't want to confuse anyone. Okay, so we're going to write the square root of 9 there. And then that's our first. Now our outer, negative 2 root 3 times negative root 7. Do you see that? This is a negative, and the root 7 has a minus in front of it, so you look at it as a negative. So negative 2 root 3 times negative root 7 is a negative times a negative. That's a positive. 2, and then square root of 3 times square root of 7 is the square root of 21. Then we need to do the outer. Negative 2 root 3 times, I just did the outer. First outer. I'm sorry. I don't need to do that. I already did it. We need to do the inner. Sorry. I lost track in my FOIL. Do the inner. 3 root 7 times 4 root 3. They both are what? What sign are they? They're both positive, so I'm going to get a plus sign here. 3 times 4 is 12, and 7 times 3 is the square root of 21. And then last, which would be 3 root 7 times negative root 7, is negative. 3 is on the outside. Root 7 times root 7 is root 49. Now we have to simplify the radicals. The square root of 9 is what? 3, so that's negative 8 times 3. You can add these two together because they're like terms. 2 roots of 21 plus 12 roots of 21 is 14 root 21. Remember, you don't change what's under the radical if you're adding like terms. And then 3 times the square root of 49 is 3 times 7. And I brought my minus sign down. So I will get negative 24 plus 14 root 21 minus 21. Do you see that there are 2 more terms that can be added together? The 2 numbers, negative 24 and negative 21, both negative. So you add the numbers, keep the negative sign. That's going to be negative 45 plus 14 root 21. 21 does not have any perfect square factors in it, so that's my final answer. Okay, let me give you one to do. Square root of 3 minus the square root of 10 times 10 root 3 plus 3 root 10. Be careful with your signs and be careful with what's on the outside and what's on the inside. All right, let's work this one together. First term times first term, the square root of 3 times 10 root 3. The 10 is on the outside, so it stays on the outside. Root 3 times root 3 is root 9 because 3 times 3 is 9. Outer, square root of 3 times 3 root 10. Both are positive. The 3 is on the outside. There's nothing here except a 1, so it's 3. And then root 3 times root 10 is root 30. The inner, negative root 10 times 10 root 3. Notice I said negative. That is the sign of this term. So you must consider it as you multiply. So negative root 10 times positive 10 root 3 is negative 10 root 30 because 10 times 3 is 30. And then last, negative root 10 times positive 3 root 10 is negative 3 root 100. You should be catching on. When you multiply a radical times itself, you're going to end up with just what's under there. So the square root of 3 times the square root of 3 is the square root of 9, which is 3 without the radical, okay? So this would be 10 times 3 plus, well, hold on. Let me not say plus yet. Do you see some like terms here in the middle? Positive 3 root 30 and negative 10 root 30 are like terms that you can add together. Positive 3 and negative 10 make negative 7 roots of 30. So you add their coefficients and you keep their radical. Minus 3 times the square root of 100 is 10. So I get 30 minus 7 root 30 minus 30. What happens? Is that what happened with y'all? Okay, I haven't worked it yet, so I don't want to mess it up. And I'm just left with negative 7 root 30. Any questions on that or any of those steps? All right. Sometimes we have things that are not binomials times binomials. They are not monomials times binomials, so not a one term times a many term or not a two term times a two term, but maybe a two term times a three term. So a binomial times a trinomial. So that's what we're going to be looking at next. This is actually number 12 on page 401 if you want to fill it in your worksheet, in your workbook, excuse me. So 2 plus the square root of x times 3 minus the square root of x minus the square root of y. So I am going to take everything, I'm going to take this 2 from my first quantity, and I'm going to distribute it to all 3 terms in the second quantity. And then I'm going to take the square root of x and do the same thing. And then they will all have been multiplied times each other. Okay? So 2 times 3, and I'll write every step for you. And then positive 2 times negative root x, that's negative 2 root x. So I'm distributing the 2 to everything. Positive 2 times negative root y is negative 2 root y. And then you do the same with the last term. So positive root x times 3 is plus 3 root x. Positive root x times negative root x is negative square root x to the second, because x times x is x to the second. And then positive root x times negative root y is negative root xy. So we're going to come through and simplify. I get 6. Negative 2 root x and plus 3 root x is plus 1 square root of x. So if you want to mark them off as you do them, there's nothing wrong with that, so you don't get lost in the problem. This one does not have a like term. This does simplify. The square root of x squared is x. And then that one does not have a like term either. That's as simple as you can get your answer, because none of these are like terms. This is the square root of x, that's the square root of y, that's the square root of x times y, that's just an x, that's just a number. Okay, so at this point, we are wanting you to start picking up on what Ronnie had said a minute ago. If you're multiplying the square root of x times the square root of x, the answer is x. Okay? If you're multiplying the square root of 3 times the square root of 3, the answer will be 3. Because you have the square root of 9, which simplifies to the whole number 3. So you want to start picking that up. Okay, so if I have the square root of 15 squared, which means the square root of 15 times the square root of 15, what's the answer? 15. Right? The squaring and the square root cancel each other out, if you will allow me to say that. Okay? They undo each other.
If it was a negative square root of 15, does the negative stay?
Where would you put it? Tell me where you want it, and then I can tell you what it does.
It's on the outside of the bracket.
Okay, so it looks like this.
Yes, ma'am.
Would it be in the parentheses? Well, then you square it too. A negative squared is a positive. That's like a negative 1 out there. So negative 1 squared is positive 1 times root 15 squared is 15, so the answer is just 15. Now here is where I think what you were trying to get at. If it was like this, you're only squaring the root 15 and the negative is hanging out front. See, the negative is not in the parentheses being squared. Okay? So that's a good question. All right, what about this? The fourth root of mn all to the fourth power. What happens with that fourth root and that fourth power? Look at the green. What happens? They're gone, and you're left with mn. Okay, what about the square root of a plus 8 squared? What's the answer? A plus 8. Nothing to show, right? They undo each other. Now, this is all well and good, but we have to be able to discern between situations. So this is the square root of a binomial, all raised to the second power. This is not. That is not the square root of one quantity raised to the second power. That is the square root of z plus 7 outside the radical being squared. This is a different case. This means the square root of z plus 7 times the square root of z plus 7. You cannot just square each term and tell me the answer is z plus 49. That is not true, okay? Because these are two individual terms, not under one radical. They're two separate terms. You have to FOIL this out. So the square root of z times the square root of z is z. Then the outer is plus 7 square root of z. And the inner is plus 7 square root of z. And the last is plus 49. So what happens is students get the first term and the last term right, and they miss that middle term every time because they don't recognize that it is actually a binomial squared. And that would be the answer to that. very tricky. Very, very tricky. Now, some of these get really hard, and I am not going to give you really hard ones on your test, on your exam, okay? And I'm going to give you all right, so let's do one that's kind of a challenge. So we have the square root of 3m minus 2, all under the radical, then a minus 5 outside the radical being squared. So this is what I'm referring to. This is a little more of a challenge, okay? This means that you are doing the square root of 3m minus 2 minus 5 times itself. And you're going to FOIL it. So the square root of 3m minus 2 times the square root of 3m minus 2 is just what? The square root of something times itself is always what's under the radical, right? So the square root of 3m minus 2 times the square root of 3m minus 2, you should be saying 3m minus 2. That's your first. Then your outer. Negative 5 times the square root of 3m minus 2 is minus 5 on the square root of 3m minus 2. Then your inner is the same thing because it's the same two numbers that you're multiplying. So you have to write it twice. And then your last is negative 5 times negative 5, which is positive 25. The only like terms I see are here and here. And this one and this one. So I'll bring the 3m down because there is no like term. Negative 2 plus 25 is positive 23. Negative 5 on the square root of 3m minus 2, and another negative 5 is negative 10 on the square root of 3m minus 2. There's no really good way to write these, so that's fine. I think your program will take it in any order. All right, we talked about a concept of conjugates way back near the first or second week of school. So we're going to practice multiplying conjugates that contain radicals. So 2 root 5 minus 7 times 2 root 5 plus 7. So conjugates are the same binomial, one with a plus, one with a minus. Usually we call these a sum and difference. Now we learned shortcuts for multiplying this and this the first week of school. I doubt that you would have them stored away readily since it's been several weeks ago, and you probably haven't worked on it in a while. So we can go through the whole FOIL process here, but you're going to see something interesting happen, and it will happen every time you multiply conjugates, and hopefully it'll come back when I show you. So 2 root 5 times 2 root 5 is 4 root 25, which is just 5. Is that okay that I did that? Maybe I should come over here and write. That's 4 on the square root of 25. And so I just wrote a little simplified down here. And then outer be 2 root 5 times 7. That's plus 14 root 5. Inner, negative root 7 times 2 root 5. That's negative 14 root 5. That's where you should take note of what's happening. And then negative 7 times positive 7 is negative 49. What happens here in the middle? They cancel. They do it every time you multiply conjugates, which is why we really only need to do the first and the last product, because the O and the I cancel out when you multiply conjugates. So we just do the F and the L, FLA, instead of FOIL on conjugates, okay? And 4 times 5 is 20, and 20 minus 49 is negative 29. Okay, you know, we talked about last week that you couldn't multiply radicals unless their indices were the same. Their index, their little number right here. But I think that I mentioned to you there was a way to do it, but we just weren't going into it right away. And so that's what we're going to do tonight. We're going to multiply radicals with different indices, and I'm going to show you how to do that. So if you have the 4th root of 7 times the square root of 7, up until this point, we've said can't do it, okay? Now, I'm going to show you how to do it with rational exponents. So the first thing you do is you change each radical to a rational exponent. Remember, the exponent on this 7 is 1. So you take the exponent over the index as the power of that 7. And this would be 7 to the 1/2. I wrote 8 because that's what I'm about to get. Sorry. My brain's working ahead of my hand. Okay. Now, how do you multiply like bases? What's the rule for multiplying like bases? You keep the base and you add the exponents. 1/4 plus 1/2. In order to add them, they have to have a common denominator. That's what my brain was doing. Common denominator of 4 and 2 is 8. Four times 2 makes 8, so 2 times 1 is 2. 2 times 4, so 4 times 1 is 4. So I'm running out of room here. I'm going to get 7 to the 6/8 power. That reduces to 7 to the 3/4 power. And your final answer, written back in radical form, is the 4th root of 7 to the 3rd. You can simplify that if you want to by taking 7 to the 3rd power, whatever it is. I'm not going to fool with it. But there's a typo on number 23 on page 404 in your book. So if you're following along, number 23 on page 404, that is a huge typo in that problem that says the square root of 5, and then they use it as 2. You need to put an X through it. It's wrong, okay? I don't want you looking at it as an example. It looks like they stopped here for their example, even though their example's wrong. It looks like they stopped there. I would probably go ahead and take whatever 7 to the third is and write it in there. Okay, let's do another one of those. The fourth root of 5 times the square root of 2. What's the exponent on 5? What's the exponent right here? 1. So this is 5 to the 1/4 times 2 to the 1/2, because there's an understood 2 right here is the index. I should have picked a different one. Oh well, I didn't. All right, so 1/4 plus 1/2. No, I can't do it. Why can't I do it? Huh? They don't have like bases, do they? They don't have like bases. So in which case, you will get their exponents to have the same denominator, but you cannot add them together. So we're going to rewrite this as 5 to the 2/8. I'm going to show you why you're doing this. Times 2 to the 4/8. Okay. So because they have like denominators now, you can rewrite that as the 8th root of 5 squared times 2 to the 4th. And I would multiply that out. I can't believe they want us to stop here. I would do 25 times 16 and get the 8th root of whatever that is. So you see what I did was get the common denominator, even though I couldn't add the exponents together because the bases are different. And then I said, well, my whole goal was to put this underneath one radical with a like index, okay? And so I achieved that because the denominator of my fractions is the index of my radical, and then 5 squared and 2 to the 4th go underneath there. And like I said, this is where it's stopping in your book, so I'm going to stop there, but you could simplify it into 25 times 16. So we could write that as the 8th root of 400. 2 times 2, yeah. Okay? Okay, we're going to pause here.